Hello everyone, I am Raymond Muller. I am a PhD student from the PerSec Security Group at Purdue University, and I will be on the industrial job market hopefully next year. This work was done in collaboration with my co-authors from the University of Arizona, Virginia Tech, and Qualcomm. So today I'll be presenting the first defense designed to combat attacks against object tracking. We call it VOGUES, Validation of Object Guise Using Estimated Components. We developed a system to extract fine-grained appearance detail from objects and compare it to coarse-grained detail from object detection and tracking in order to detect attacks via inconsistency between the two. So as a background, this is the typical perception pipeline of an autonomous system. It's used in things like autonomous driving, mobile robot navigation, and automated surveillance. The goal is to take data from visual sensors, such as a camera, and extract usable information that can be used to make a decision. So given images captured in a sequence, we start with object detection, which outputs bounding boxes, which show where in the image objects are, as well as the object class, which tells you the type of object, such as is it a car or is it a person. After that, we pass that information into object tracking, which aggregates results over time in order to produce trackers, which have a trajectory and a unique object ID for each object, as well as a bounding box as its own. Essentially, object tracking uses knowledge about the movement of the same objects over time in order to create an accurate prediction of where the object is over a sequence of images. Finally, the information from object tracking and object detection are passed into fusion, planning, and control so that the system can make the final decision on what action to take. So what might an attacker do to disrupt this pipeline? So let's first look at attacks that target object detection specifically that we examined in our work. So the first attack is object deletion. This is very simple. An attacker just deletes the bounding box of an object, causing it to disappear from perception, which can be very bad. In this example over here, we have a pedestrian crossing a road, and it's deleted. So if there's an autonomous vehicle here, it might hit that pedestrian and get into legal trouble. The next attack is object misclassification. This is changing the class of an object in order to cause planning irregularity. So for example, if I change a stop sign into a speed limit 120 miles per hour sign, the car might think it has to speed up. It's going to blow through the intersection, maybe crash into something. There are also object tracking attacks. So object tracking seeks to have a more accurate bounding box, so it provides some resistance against these kinds of object detection attacks. However, an attacker can directly attack object tracking directly in order to circumvent that. So the first attack an attacker might do is cooling shrinking. Cooling shrinking suppresses all of the tracking results over multiple frames, essentially making object tracking stop working. An attacker might use this to, for example, disguise unauthorized entry into a restricted area. The next attack is called tracker hijacking. In tracker hijacking, you take control of the movement of a bounding box and make it go where you want to go over a set number of frames. So in this example here, if I'm following a vehicle in front of me and an object tracking or tracker hijacking attack moves that vehicle's bounding box out of my way, I might think that the way is clear, I'll speed up and I will hit that vehicle in front of me. So to address object tracking attacks, we designed VOGUES, the first work detecting tracker hijacking and cooling shrinking attacks against OT. VOGUES relies on the principle of component consistency. If I can see an object, then the object parts should be visible as well. This is sort of basic human reasoning. If I can see something, but I don't see any parts of that something, either I'm hallucinating, I didn't sleep enough, or something is wrong, right? So VOGUES takes in both the OD and OT results as well as the input frames, and it checks to see if that principle is enforced. First, we do component reconstruction, which isolates object instances, extracts details through pose extraction, then compares these details with object detection and object tracking results through bipartite matching. And if there's an inconsistency, we sound an alert. But what if the attacker tries to change VOGUES results, this component reconstruction, as well as whatever they're trying to change with the attack? To guard against this, we have reconstruction validation, which is an LSTM network that ensures that the appearance of details over multiple frames is consistent with what we might expect. So for VOGUES' first step, we isolate object instances in order to cut down outside factors that could influence our component extraction. But how do we do that object isolation? We use two methods. The first method is through region proposal networks, which is split into two stages. So we take the input image, we slide over that image, and we produce a feature map. So this feature map is sort of like a heat map that determines where in my image are objects likely to be. So that might return multiple regions. In order to get the final region, we use a regression to select the area that has the most pixels or features that indicate a target, and then we regress that coordinate space into a tight bounding box. And this is going to be what is returned as the cropped region by our object isolation algorithm. One key challenge of region proposal networks, though, is that it doesn't work very well for objects that are dispersed among crowds or at long distances, such as pedestrians. Therefore, for objects like this, we apply the spatial transformer network, or STN. So for STN, what we are doing is we are providing parameters theta that can transform the original coordinate space G into a cropped coordinate space that only has our isolated object. We do this via affine transformation. We ensure that the original coordinates, xb and yb, are equal to the theta parameters matrix multiplied by the coordinates after the transformation. By solving that equation, we can use the theta parameters in matrix multiplication to convert any sort of input or operations from one coordinate space to another. So we use that, we pass it into a localization net, and we can transform something where we have an object to isolate into its cropped instance. Once we have individual objects isolated, how do we do component extraction to get the component sets? So the first step is defining what a component set is. This might seem intuitive, but it's important because different classes of objects look different. So we take the approach of defining key points and their relationship to each other. For pedestrians, the key point would be like the head, the chest, the shoulder, the arm. For cars, it would be the bumpers, the windshield, things like that. All of these potentially important points are what we call key points. And they are given different subclasses. So when I say that this is a head and this is a chest, those are considered different classes. That's important because we need to define the relationships between key points. The head is connected to the neck, or the bumpers are connected to the windshield, things like that. So the definition of objects details can be very rigorous, and we have a set of points and edges that encode exactly how an object should look. So in order to actually find these points, we solve a classification problem. We train a fully convolutional network, and we formulate the loss function to extract the key points based on appearance. So basically, loss function, we try to optimize so that our predicted points are as close to the ground truth as possible. At runtime, our fully convolutional network extracts key points from an isolated instance, and the highest confidence results are picked. So we have a set of points. Then we connect those points based on those rules that I defined earlier, like the head and chest. If I have these 2 points, I will connect them automatically and have that full component set. To actually detect attacks, VOGUES relies on component consistency as a principle. Once again, all of my components should correspond to a bounding box and vice versa. So how do we actually measure that discretely? First, once we have a component set, we need to extract the bounds of the component. So if we see this red box over here, we take the maximal and the minimal bounds in the x and y coordinates in order to determine what area that my component set covers. Then we construct a match graph. We have every component set over on this horizontal column and every bounding box in the, this column over here. And we construct a match graph using the intersection over union, which indicates how much of each bounding box overlaps with the component set and vice versa. Then we conduct maximum bipartite matching to ensure that there is a one-to-one correspondence between the bounding box and component set. So each bounding box has one component set. If we cannot find a maximum bipartite matching, this indicates that there is an attack going on and we sound an alert. In this case, this bounding box cannot be matched with any component set because it's being moved off in a tracker hijacking attack, so we raise the alert here. So obviously our extraction and isolation process are both neural network based. What if an attacker tries to attack our approach to component extraction at the same time as they conduct their attack? So they will try to move our extracted components into the same area and look consistent. Well, a key observation is that it's very hard to hijack an entire component set because each of these points are different classes. That means that the attacker needs to individually take each of those points and move them in a consistent manner. So previous work has studied this extensively, and they found these weird behaviors. Because each of these key points, it has a different sensitivity to an attack, they'll be moved in sort of different magnitudes. So you end up getting like weird like yoga poses and like broken bones and stuff that really don't make any sense. So in order to make this kind of adaptive attack as hard as possible, what we do is we perform what we call reconstruction validation. We want to ensure that for each time frame, the component sets are moving in a manner consistent with their previous behavior. There's no weird sudden joint locks or flailing motions in the middle of the motion. So formally, we use an LSTM validator to ensure that over time, the behavior we see out of the components is consistent against previous data that we collected and trained the LSTM on. So every time we compute a new feature vector V over here, it updates the part of the parameters R theta that are recurrent in an LSTM, which are subject to change. So the informal word you can think of this as is memory cells. They allow the LSTM to remember sort of what came before. During each step, as shown in the equation over here, the vector at time I is influenced not only by the raw feature set that it extracts from the current time, but also by the previous feature vector. And then the final feature vector is passed into a fully connected layer, and it checks to see that if over time this motion is about what we expect. If it's at least 50% confident that the sequence of component sets makes sense, we say that it's valid and continue. Otherwise, we sound an alert that there may be an attack. So to evaluate VOGUES, we conducted object detection and object tracking attacks against YOLO v3 for our object detector and distractor-aware Siamese region proposal networks for our object tracker. I'll talk more about what attacks we did exactly on the next slide. But we evaluated both non-adaptive attacks, which were taken directly as proposed by previous work and previously demonstrated, as well as adaptive attacks, where we use those same attacks, but now we add an extra goal such that the attacker will try to evade our defense at the same time as they achieve their attack goals. So for digital attacks, we used BD100K and MPII for our vehicles dataset and surveillance dataset respectively. And we also conducted real-world experiments out around our campus for object tracking and object detection attacks. So we evaluated VOGUES on tracker hijacking and cooling shrinking attacks as designed, and also against those two object detection attacks that it happens to work on, misclassification and deletion. So we can understand that deletion is similar to cooling shrinking, and misclassification, if you have a person's bounding box and a car's components and vice versa, obviously something's wrong. So it'll sort of detect it by default. So we find that VOGUES has an average attack detection rate of about 96.78% for all 4 of the attacks, and a false positive rate of only 3.29%. We find that in the digital domain, performance is quite consistent, which makes sense, because in the digital domain, there are less environmental factors, poor lighting, complete darkness, things like that can throw off a component reconstruction. The same high consistent performance is also found in real-world pedestrian attacks against surveillance. So in surveillance, lighting conditions tend to be very bright and stable because the surveillance system wants to be able to see the person and if they're committing a crime, things like that. So our performance is a little lower against real-world attacks against vehicles, because in the autonomous vehicle domain, there are a lot more environmental factors that can come into play. Finally, we also evaluate adaptive attacks where the attacker attempts to evade our defense at the same time of achieving the attacks. We find that they need to be about 30 times brighter than non-adaptive attacks in order to work, which is quite extreme. You can see how that looks on the left. Like the noise required is completely overpowering the original image and it's highly visible. We need to change a lot. So when we tried to do this in the physical domain, we weren't able to really fully suppress or achieve the attack goals in any of our cases that we tried. So you can see here that some of this person's components are suppressed, like their entire torso is gone, their head is gone, but we can still reconstruct their shoulder, their arm, and their hand, which is sufficient enough to detect that this is a tracker hijacking attack that's moving the bounding box from this right side over here onto the left. And finally, within simulation settings, we found that 15% of adaptive attacks cannot be achieved because of a lack of attack surfaces. So because there are much greater perturbations required in order to achieve this adaptive attack, it becomes very sensitive to some of those real-world attack considerations, like what surfaces can you use to perturb and what kind of resources that you have in order to affect those perturbations. So in summary, we present VOGUES, the first practical countermeasure against tracker hijacking and cooling shrinking attacks against object tracking. It's also effective against misclassification and deletion attacks against object detection. And we use a robustness validator to increase the difficulty of adaptive attacks by ensuring that components that we extract are consistent over time. Thank you for attending. I will be happy to take any questions now.